Esto así. Ok, listo. Así vamos a hacer así. Listo.
Bueno, buenas tardes. Voy a presentar a nuestro invitado en inglés y luego pues la presentación va a ser en inglés, aunque está aprendiendo español, ¿verdad? No. Pero ¿puedo presentarte en español o inglés?
No, inglés.
Sí, no, pero yo presentar a ti.
Ok, sí.
Ok. Pues nuestro invitado de hoy es alguien que nos visita desde Austria, de la Universidad de Graz. Está aquí porque tenemos un convenio, una colaboración desde el año pasado de un proyecto que se llama Dinosaur. Tenemos varios estudiantes nuestros en instituciones en Europa, en este momento 3 de ellos están en Europa, y ahora tenemos la visita acá de la contrapartida austriaca. Esperamos que vengan muchos más, pero nuestro invitado de hoy es Christoph, así lo Schirninger, es de la Universidad de Austria, como ya dije, de la Universidad de Graz, es austriaco. Y bueno, hoy nos va a hablar sobre un tema muy interesante, muy pertinente y con muchísimas perspectivas, no solo para la astrofísica solar, sino para todas las áreas de investigación. Va a hablar de aplicaciones de inteligencia artificial a la física solar, pero yo creo que acá podemos extraer muchas ideas para muchos temas de investigación de lo que hacemos nosotros en astrofísica. Así que tengo muchas ganas de escuchar los trabajos de él porque lleva muchos años trabajando en el desarrollo de algoritmos y su tesis de doctorado, que está próxima a terminar, también es en el área de Machine Learning en astrofísica solar. Así que it's a pleasure to have you here. Thanks for coming, and I hope you enjoy the rest of the time you are going to do with us. Thank you very much for giving us this colloquium first. Thank you.
Thank you very much for the nice introduction. So, my name is Christoph, as Santiago already said, and this talk is about my PhD thesis, so the work I did during my PhD, which is about AI applications in solar physics. And this is specifically a talk about using AI from the photosphere up to the corona, so uppermost layer of the solar atmosphere. But before we go into the applications, let's look at how neural networks actually work and remind us a little bit about it. So basically what we have is always an input layer, we have a hidden layer here, and an output layer. And the input layer here is basically our input data feed into our network. And the hidden layer, so in green here, we have a thing which is called neuron. And this neuron is connected to the input data by these black arrows, which are called weights, or W1, W2, and W3 in this case. And in this neuron, you perform this mathematical operation, basically, where you calculate the sum of those weights multiplied by your input data. And this then goes into your output layer. And what you can do then is basically you can stack So what you can do is basically stack then multiple of these neurons together, but you still remain with an input layer. You can have a couple of hidden layers, and you have the output layer in the end. But you can see that you have a very complex architecture of this neural network now, where you have a lot of weights connected to each of the neurons here. And how you train them in these models is basically you feed in your input data into this input layer.
Sorry, Christoph, please.
No, it's not. Okay.
You have to point it.
Okay. Okay, I see. So yeah, you're feeding basically your input data through the neural network until the output layer, and you get a certain output. To optimize then your neural network, you have a target or a ground truth. And you compare your outputs from your network to your ground truth, to a target. And you calculate basically the difference between these two, which is called the loss. And when you calculate the difference, you can go to the next step, which is called back propagation. So what you do is basically you update the network to get a better output to feed the target as close as possible. And when you are as close as possible, you have a trained model and you can feed new data to get a certain output. This is basically the basic principle of how neural networks work. The most simplest case of supervised learning, which is called, so the idea is basically you get input data, you have a mapping function represented by the neural network, which maps to a certain output. Okay, so this is the basic principle of neural networks, but let's have a look at some applications I've been working on during my PhD. And the first application is about image-to-image translation, or ITI for short, to reconstruct high-resolution ground solar observations. But why do we actually need image reconstruction methods for large aperture telescopes? So we are building ever larger telescopes with the Daniel K. Lewis Solar Telescope, or DKIST for short, and the future European Solar Telescope, which are telescopes with a mirror size of up to 4 meters. We can resolve very small scales on the solar photosphere up to the solar chromosphere. And this is very important since I already played the movie on the right-hand side. You can see an observation from DKIST here on the right-hand side, where we have a lot of granulation pattern. Okay, yeah. You have a lot of granulation and you see these photospheric motions in the sun. But also when you look at the center here, you can see those bright points or these bright lanes, which are called intergranular lanes, which represent the magnetic field in the photosphere, which is important since they are a key driver of solar eruptive events, which we observe. And this helps us basically to study the sun on various spatial scales, so on the smallest scales in particular. And with this, we can also, by better understanding our sun, make the connections to other stars. But there is a problem with these large aperture telescopes. And this is, we are not diffraction limited anymore with these large aperture telescopes. And what this means is basically, and can be explained by astronomical seeing. So the basic principle behind this, if you have a distant point source, which is in our case the sun, you can consider that the incoming light waves are flat. But after passing the turbulent layer of the atmosphere, those light waves get distorted and they have phase errors. And those phase errors then enter our telescope aperture, which cause distortions and blurring in our raw image data we obtain at our telescope. Nowadays, many telescopes are equipped with adaptive optics systems, which are basically deformable mirrors trying to correct for these phase errors in the wavefronts. But there still remains some phase errors. We definitely need to correct them with post-factor reconstruction methods. And an example of such a raw image versus is shown here on the right-hand side from the 1.5 meter Brega telescope, where you can clearly see those wigglings in the raw data, and also when we compare it to the DKIST data before, the granulation pattern is not that well resolved, as well as the penumbra and the umbra of the sunspot here. So therefore, we use AI to correct for those image reconstructions or for these blurred observations. And we specifically use image-to-image translation for that, or ITI for short. And how this works is illustrated here. So we are using generative adversarial networks for that, which are GANs for short. And the training cycle of this neural network is shown in the figure here. And the principle behind this is that we start from an observation, which could be or reconstructed observation, which we refer to the domain B, and we use it as input to our generated BA, which then translates to a short exposure image burst of domain A, which is the degraded burst. And the second neural network, which is called discriminator A here, and has to distinguish between synthesized burst and a real image burst. And this information is then used as input in our generator AB to translate back to the high quality, high resolution observation of domain B, which should be again consistent with the input on the left-hand side here. Important to note here is that we're using unpaired image-to-image translation. What that means is that we don't need a spatial, nor do we need a temporal overlap of the two data sets we want to translate in between. The loss function we employ here is the reconstruction loss between the difference of this image on the right-hand side, so the output, and the input on the left-hand side. But we also have this adversarial loss, which is given by the architecture of the neural network. So the idea is to update those networks by playing more or less a minimax game. So the generator here tries to fool the discriminator A here by generating realistic raw image first. And the discriminator A then has to distinguish between true and synthesized image first. So this network tries to fool this one, but this one has to distinguish between real and synthesized until the generator produces realistic image bursts, which can then be used to reconstruct the observation. So we can look at some results here from the 1.5 meter Vega telescope, again in VG band, so at 430.7 nanometers. In the first row, you can see a single frame of the original burst. In the second row, we show the spectral reconstruction, which is a state-of-the-art reconstruction technique, which is currently used for ground-based observations. And on the bottom, we show our ITI reconstruction. And you can clearly see the difference between the first row, where we have these degraded frames, and our reconstruction from spectral and ITI. You can also zoom in into the small output region here, marked by this red box. And what we see is that spectral reconstruction and ITI looks pretty similar also on small scales. But when we talk about generative adversarial networks, we need to ask the question, where does this additional information is coming from? So therefore, we trained our neural network on a varying number of input frames, where we used 1, 5, 10, 25, 50, and 100 frames. And we compared it with the quality metrics, with the peak signal to noise ratio, or the structural similarity index, which are basically metrics to calculate the perceptual quality. And we used the mean absolute error and the mean squared error, which are diffraction quality metrics. And what we see is that we achieve the best quality for all the metrics when we use the entire image burst as input, which means the neural network effectively learns the reconstruction from the whole burst we are using, so from all the images we are using as input. Whoa, this is a bit too fast. Okay. But a big advantage of using AI, of course, is the reconstruction time. It can save a lot of time by processing data very fast. And here we show an example of how fast we can reconstruct those image bursts. For example, when you use NVIDIA A100 GPU, the reconstruction time of a single observation is on average 0.5 seconds. When you use a standard AMD CPU, which you all have in your laptops, the reconstruction time is 3.5 seconds. And when we compare it to spectral reconstruction, which is currently used, the reconstruction time can take from minutes to hours, or it can go to in days, which is a pretty long time. So, yeah. Now we have seen that we can use AI to reconstruct these observations, but in this case, like for ITI, they are always dependent on the reference ground truth data set, which is in our case the spectral reconstruction. And in the next study, we want to get independent of the reference ground truth data set, because we can always get as good as the ground truth data set. We cannot get backward signals. So therefore, we call it a neural blind deconvolution to reconstruct high-resolution ground-based observations. And before we go into how the neural network works, we need to look at the problem setting, so how the images are formed at the telescope. So what we get is basically those degraded observations, so the original image burst at the telescope, and this is given by the real object intensity distribution, so how the sun actually looks like, which is then convolved with the point spread function. And the point spread function is composed of the telescope point spread function and the atmospheric point spread function. But this is an ill-posed problem, since the only thing we know is basically what we get at the telescope aperture. We don't know the real 2D intensity, nor do we know the atmospheric point square function. So therefore, we use a neural network to estimate both of them at the same time. And this is based on neural radiance fields, which is called. So the idea is basically you start from a grid here on the left-hand side, where you sample coordinate points x and y. And these coordinate points, the neural network maps it to intensity values for each coordinate point. And then we calculate this convolution, which we have seen before, with point square functions, which are also optimized, which are like learnable parameters here. And when we calculate this convolution, we then get our predictions, which are our degraded image bursts again. And we can use our predictions then to the actual and compare it to the actual observation we obtained at our telescope, and we calculate the loss in between. And to optimize this neural network, we optimize the weights of the neural network to get better intensity distributions of the real object intensity. And we update the PSF parameters here. So we update n PSF parameters to actually get like the real point square function, which is causing the degrading of the real object intensity distribution. And to test our neural network, we use observations again from the 1.5 meter Gregor telescope, specifically from June 2022. This is again the degraded burst. You can again see how it affects the observation, the turbulent atmosphere, with this stretching and wiggling. But compared to the other observation, you can really see that the seeing for this time was pretty good. As a second testing observation, we use observations from the DTS telescope, which is the largest solar telescope we have so far. And on the right-hand side, you can see again like the burst of observations we get, which contains 80 frames here, and similar as for the Gregor observation. Those you can really see the atmospheric turbulence in those observations. So we need to apply post-factor reconstruction methods. Let's look at some results. First of all, the Gregor observations. We zoomed in into a smaller region here. So on the left-hand side, you can show again this in the frame of the original burst. In the middle panel, we show the neural PD reconstruction, and on the right-hand side, again, the spectral reconstruction here. Zooming in into this smaller props and this red and blue rectangle, we can see that the reconstruction also works very well on smaller scales, especially here in red. But zooming in into even smaller scales, where these blue boxes here, what we see is that neural PD can very fine and detailed structures, which cannot be resolved for the spectral reconstruction, for example, which looks a little bit more blurred as for the neural PD reconstruction. And for this time, we also have a second observation. Since Gregor uses a beam splitter, we get two wavelength channels at the same time. We see it for blue continuum, for example. Again, the neural PD reconstruction looks very similar to the spectral reconstruction, but also on the smaller scales, same as for G-band, we can recover like very fine detailed structures, like these bright points or these intergranular lanes of bright points between the granules here, which look a bit more blurred for the spectral reconstruction on the right-hand side. We can also look at the results. Before that, we also can, of course, obtain the point square functions, which are degrading our observations from our neural network. And what we see is basically for G-band in the first row, blue continuum in the second row, they look very similar, which is a good sign, which means we get a physically of the point square functions. There are some small differences visible here, for example, for the second one here, or for the third one, or fourth one here, but this can be caused because of the different filter channels used here.